One of the reasons for talking about thermodynamics and then focusing in on ideal gases is it gives us a system that we can do some pretty careful calculations of what happens to the energy. And this is going to be important if we want to make things more energy efficient, is to understand, yes, energy is conserved, but when does energy go towards work or electrical energy or mechanical energy? When does it go to thermal energy? When can we recover it to do useful work with things? When is it just exhaust in the form of basically thermal pollution? And so we're going to really focus on the laws, finally, of thermodynamics in here. So first of all, we need to define something that I think we've already taken as sort of a given, and that is when we have something that's in thermal equilibrium, what we really mean is when two things are in thermal equilibrium, that means their temperature is the same. Okay, T1 and T2 are the same. So when we bring two objects that are at different temperatures together and put them in an isolated system, which means they can only exchange energy with each other, then when they get to the same final temperature, we say they're in thermal equilibrium. There's not a reason for them to exchange energy anymore. And so built into that, we have sort of this idea of thermal isolation. If you wish, you can think of it as sort of a nice insulator, where we have object 1 and object 2, okay? And they can exchange energy until they get into thermal equilibrium. We have something called the Zeroth Law of Thermodynamics, which kind of feels like it's sort of a given, but it's important. The Zeroth Law is that if you have two objects, if 1 and 2, say T1 and T2 are equal, and T1 is equal to T3, like we take this out and put it in a box with T3, then that means T2 and T3 have the same temperature. Okay, so that's sort of a, well, yeah, that's how equality works, but it's important because it's a way of, that's really what thermometers are doing. They're measuring the temperature here, comparing it with a reference, and then we can say, oh, those are the same. What that means is that it's not that their internal energy is the same, but their average, if they're ideal gases, then all that internal energy is just an average kinetic energy. They have the same average kinetic energy. Obviously, the number of particles tells you the total internal energy. Okay, so having said that, what we're going to do is really focus on these ideal gases. And what I want to do is have us look at work in particular. So we're going to connect, how does work connect to internal energy? So that's sort of our step here. And so the idea, if you remember back from Physics 1, is that work was force times a displacement in the direction of the displacement. But sometimes that force wasn't constant. So we had some definitions of work. We had work was equal to F times D times cosine of the angle between them, or F dot D for constant force. This was for constant force. If we have a varying force, we had work was equal to integral F dot R or F dot X dx or something like that. And this is the one we're going to be working with. So in fact, we can say it looks like this, or a little bit of work, a differential of work is equal to F dot dr, okay? Or we can write it as F times some small displacement, I'm going to call it dx because we're used to doing integrals with x, times cosine of the angle between the force and the displacement. So here's our setup. We're going to set up a container that has gas in it, which is capped by a piston, and this piston is sealed, but it can slide up and down, which is a little bit of a trick. You can get sort of very close to this with some graphite in there, and it can seal, and the idea is that it moves without friction. Well, it has to be a little bit of friction if it's keeping the gas inside. So basically we have these gas ideal gas particles, so they're tiny, and they're hitting on this piston, and we could say that this would be doing work if the gas moved the piston off that way. The force on the piston is this direction, right? That's the direction of the force. So if we have a displacement in the same direction, right, a dx, so that it comes to this new location, there's our dx, then we could say that that would be the work done. So we can say the little bit of work that's done is equal to whatever force is applied by the gas times this dx. So this is force by the gas, and this is a little bit of displacement. And of course, with gases, as we saw when we worked with fluid dynamics, instead of forces, we work with pressure, right? So pressure is force. Force. Pressure is force. Pressure is force over area. So in place of this force, we can rewrite force is equal to pressure times area. And so we can put that in there, and we'll have that. The little bit of work that gets done is pressure times area times dx. This area times dx, we're talking about the area of the piston, so it might be a cylinder. Cylindrically shaped piston, and so that would be this surface area here, right? And so this is actually, then if you take the surface area times this, that's the amount the volume has changed, okay? So we can have our work is equal to pressure times the change in volume. That's the change in work. Or the definition we'll be using, the useful definition is that the work done by the gas is equal to the integral pressure dV from some initial V1 to V2. Okay, so maybe this is 1 to our new volume 2, and the volume could be fairly big. So this is kind of a weird, we're used to an integral with x's or y's or thetas or something like that, and it really depends. Is pressure constant? Is pressure changing? What's going on? So we're going to look at a couple of different examples of what we're looking at in terms of doing this integral. Okay, so a reminder, this is work done by the gas. For example, work done to expand this piston. So we're going to take the first case we're going to look at is we'll look at the case where this is in thermal isolation. Well, it's not. It's we're going to take a look at the first case where we keep this at a constant temperature. So it's maybe isolated from an environment, but connected to some kind of a heat reservoir, so that, or a thermal reservoir, so that this part always stays at the same temperature. Okay, so you can think of it as at a constant temperature. So we're at a constant temperature. So if we look at, we'll use PV equals nRT, and we're going to be using this a lot. So keep this in handy. I should probably list it as one of our important equations, but you know this, or capital N KBT. Either way, I'll use it in this notation because you're probably more familiar with it like this. Then the work is equal to, if we've got constant T, then this, and the number of particles is constant because we've trapped them in there, then that whole thing is constant, and I can rewrite my P as nRT, which is a constant over V, right? That's a constant. So it would be nRT over V dV from this 0.1 to 0.2 that we're interested in. Now, I can pull out constants, N, R, and T. We said that the temperature is staying constant of this because it's connected to some kind of reservoir that keeps it at the same temperature. And then we have the integral of dV over V from 1 to 2. Now this is where I need to remind you of a little bit of calculus here. You probably remember, I hope, you have something like integral of x to the n dx. That's equal to x to the n plus 1 over n plus 1. That's our power rule. In this case, our n, this would be an integral we're looking at, v to the minus 1 dv, but it could be x. Then this would be looking like v to the 0th power divided by 0. So this one you don't do like this, right? And you can't do it like that. Well, you can still write it like this. I hope you remember this is that special case. So this is true except for unless n is equal to -1. And then we have this. If you prefer, if you don't like it to be v's, you can make it x's there, natural log of x. Okay, so this work suddenly becomes, I'm doing the integral, I've got n RT that still sits out there, natural log of v evaluated from 1 to 2, or volume 1 to volume 2, I guess I'll do it, the initial and the final. And so this becomes, putting in, remembering our rules for definite integrals, this is nRT. I can substitute this into here. It becomes natural log of v2 minus natural log of v1. If you don't really remember the rules of definite integrals, all you do is you substitute the first value in, subtract it, and put in the second value, just like I've done here. Now I can further simplify this. Another mathematical rule, this is a lot of math, is that natural log of A plus natural log of B, you may remember this, is equal to natural log of A times B, right? Natural log of A minus natural log of B is going to be natural log of A over B. I hope that's looking vaguely familiar. As long as we're doing this, we might as well say 2 natural log of A is also equal to natural log of A squared. You can show it from this first one, but these are some of our natural log rules. We are going to run into natural logs a good bit, so just get ready. And that's nRT, natural log of V2 over V1. So that's the work done if we've held the temperature constant. Okay, so this is our constant temperature example. We can also look at the situation where the pressure is constant and the temperature changes. This is maybe what you thought of initially with this setup, and that is we increase the temperature and therefore the volume increases, temperature volume increases if the pressure stays the same. For example, if we just let this piston move and we keep the atmospheric pressure the same, that's a fairly common setup. Okay, that's what's happening if you take like a balloon and heat it up. Pressure's basically the same. And so if pressure is constant, then our work, this integral pressure dV from 1 to 2, notice that if pressure is constant, we can just pull it out. This is an easy integral. See, I did the hard one first. 1 to 2 dV, and the integral of dV is just V. This equals P, V, evaluated from, we'll say V1 to V2, or the work done is pressure times V2 minus V1. Now this is an interesting thing, minus V1. You may argue with me that it's super interesting, but if the temperature is constant, we got one value of work going from 1 to 2. If the pressure is constant, we got a different value of work. So the work done going from 1 to 2 depends on how we get from 1 to 2. The work is path dependent. There's not going to be a potential energy associated. Okay, so this is a pressure volume graph. The reason we draw a lot of these, if this is my volume 1 to volume 2, and we go along this path, this is going to be my blue or by the time I got finished sort of orange, this is the area under the curve that's described by this equation. Okay, that's my area under the curve for this isotherm. This is a constant temperature. This is my T is constant. The area for this green one is going to be, suppose we did it at constant pressure. Well, if pressure is constant, I keep the same value. I go from V1 to V2. I go like this. That's the work done in this green area. Okay, so that's the green area. That's this one. Now, to get back to the same point, so I started at point 1 with pressure 1, V1, temperature. And if I want to get back to this point 2, which is pressure 2, volume 2, same temperature, I can take P constant, which is that, and then I can take one more step, which is to calculate the work done to go along here. So this is path 1, step 1. Step 1, and I guess I should call it step A because we already have a volume 1 and volume 2. So this is step A, followed by step B. And the work done for step B, work for B, is equal to 0 because there's no area under the curve. If you like, our V doesn't change. dV is equal to 0, so there is no work done. So we can get from this point 1 to point 2 sort of two different ways with two different amounts of work. We can go along the isotherm, the constant temperature, that's this path, and we get this amount of work. Or we can go along this way. We can hold the pressure constant, increase the temperature, and then, this is a weird one, we hold the volume constant. So on our piston, we hold it sealed. We hold it at the size that it is, and then we reduce the temperature, which reduces the pressure inside. Okay, and the way we can do that is with our piston situation, is that once it's expanded to point 2, we can lock it in place with a pin or something like that, and then we can lower the temperature. And as we do this with PV equals nRT, if V is fixed and we drop this temperature, then we're obviously going to drop the pressure because we're lowering the kinetic energy. It's not going to hit, we don't have as high a V, so we don't have as high momentum that's exchanging with the walls to have as high a pressure. Okay, so the point is I can go from point 1 to point 2, and I can have different amounts of work done, different paths, but I can have the same change in internal energy. So my change in internal energy from the internal energy of point 1 is going to be 3/2, and we didn't change the number of particles, K times T1, and the internal energy at point 2 is going to be the same no matter which path we took. But I said energy was conserved. So we had work that was energy. We have internal energy. Internal energy is fixed. Work is different depending on the paths. So there's one other energy exchange we have to build into this for energy to be conserved, and that is the heat. And so that's going to get us to the first law of thermodynamics and the next video.